Alrighty, guys, welcome back. Um, Today we're going to be talking about mass wasting, landslides, debris flows, all that fun stuff. Um, your grades are posted for your exam 2. Those grades have been curved, so that's the final grade for that one. Uh, For those of you that have stuff missing on Canvas, I have unlocked those for you. So you have until the end of this week to get those in. So please do get those in. You have an in-class exercise that's due on climate change. That's on the Canvas site as well. So keep that in mind. Real quick, easy project, should not take you long at all. And have exam 3 at the end of the week. Same deal as exam 2, written on paper in here. Because that is the last day of the class, I cannot accommodate any other days to take the exam. Unless you're taking the exam early, that's great. But otherwise, I can't ask you to come in sometime next week because I, like you, am also a student. I have classes starting next week. So I'm not going to be able to administer an exam and give out those accommodations. So make sure you can, if you can't make it on Friday, you're gonna have to take the exam earlier. So plan accordingly. I think that's all housekeeping stuff. I think. Any questions on stuff before we get started? No. All righty. So this week we're talking about mass wasting. Started by talking about soils, subsidence, and how soils form, and understanding how soils form, and understanding sediment and soil deposits is going to help us understand how mass wasting happens, how mass wasting can occur. So this is in Savona, Italy, a couple of years ago. This was a big debris flow from the top of this hill slope. This area of Italy is known for its many, many rolling hills. So there was a lot of, after a period of heavy rain, all of this soil just slumped and mixed in with the water. So you get more of a fluid flowed right into this road, cut off the road completely. And it also dug out stuff underneath that bridge there. So that helped cause the road to collapse. So this is the kind of stuff that we're dealing with when we talk about mass wasting. We have a lot of them occur around the world, pretty frequent, and they're tied to a number of things that we've talked about already, and we're going to discuss that as we go. So we have 3 specific types of movement when we're talking about mass wasting. Mass wasting is just the removal of some large mass of, that could be rock, sediment, soil, from one place to another, usually due to gravity, due to fluids, due to some external forcing down a slope. So we have falling, which is just free fall of earth material. So rock falls happen a lot whenever you have steep cliff sides. That's just stuff falling from the top as tumbling is blocked. Most of that is due to those weathering and erosive processes we've talked about, that exfoliation, frost wedging, stuff like that, where stuff's pushing those blocks of rock apart and they're going to fall due to gravity. We can have sliding, which is the movement of material as a cohesive, coherent block. So the whole thing is moving as a single unit, rather than rock fall, where you have a couple of rocks fall. Maybe you have a bunch of them fall at the same time, but it's not a cohesive unit. It's just a bunch of jumbled up rocks together. For sliding, you have the entire motion of the entire block. And that happens along a specific plane. Usually that plane is straight along the steep slope. So we can have that a block of soil or a block of rock, like a piece of bedrock formation that can slide along the slide plane. And then we have flows, and that's the movement of unconsolidated material with mixing. So this is where we're getting more into the precipitation, the water. The more fluids we inject into the soil, the more like a fluid it's going to behave. So this is where we're moving into mudslides, landslides, debris flows. And those can be pretty devastating. So we're going to talk about each of these. So we mentioned rock falls before. I mentioned when we were talking about exfoliation, where those external pressures are just popping the rocks off the side of the rock face, much like when you exfoliate your skin, you're getting rid of those dead skin cells. All of those flakes of rock are going to pop off of these huge granite cliffs, and they're going to fall and tumble with gravity. So this happened at Yosemite's Half Dome, makes it a lot difficult to climb because it's changing the surface of the rock, changing where all the handholds are, so you're not going to be able to use them anymore. So this is mainly due to ice wedging and exfoliation. Ice wedging, remember, is where we get water in between those cracks, all those fractures, and water expands whenever it freezes. So as it's freezing, it's going to expand and push and direct pressure on the outside of the rock. We also have thermal expansion and contraction. Remember, different materials are always going to expand when they're introduced to heat. So heat always energizes the molecules, makes them want to spread apart. So think of your high school science class or even middle school science class where you talked about solids, liquids, and gases, how far apart those atoms are whenever they're in those different states. Gases are under the hottest temperatures, so they're going to be much, much further apart. So as you increase heat, you're going to spread stuff apart, you're going to expand. Okay, so let's start with rock slide. So this is where we have cohesive blocks of material moving along a slide plane. So in this specific example, we have different layers of bedrock. Maybe it looks like a limestone at the bottom, maybe some blocks of sandstone or shale on top. So all of the shale on top is moving as one unit along that limestone at the bottom. So remember, we have our laws of original horizontality and our laws of superposition. So the stuff at the bottom is older, and then that stuff solidified, turned into rock, stuff deposited on top of that, solidified, turned into rock. So those bedding planes where those different layers are meeting, that's a really weak surface. They're not bonded together. As opposed to anywhere within the formation, they're a lot more cohesive. They're going to tend to stay together. Along those bedding planes, it's a lot weaker, so they're going to tend to separate and fracture along those bedding planes. So as we tilt that surface, remember, we always deposit in horizontal layers. We have to enact some force to end up tipping it and deform the surface. So as we tip it and create a hill slope, we're going to start introducing some new forces and vectors of forces to that specific block. So the bedding plane below it acts just like a sliding board. It's going to be a surface that top overlying layer can just slide right down. The important things about these is these happen like that. They don't happen slowly over time. There's a separation and boom, gravity takes hold and it's going to pull it all the way down. So these are really, really devastating because it's just a wall of rock. This is in Gros Ventre. This is a rock slide that happened. So we have some stream channel at the bottom of this slope. We have these limestone and shale units underlying the sandstone unit. And you can see that those bedrock formations are matching almost perfectly parallel to the actual slope of the hill. That doesn't always happen, but when it does, that's going to increase the risk that we have of rock slide. So if those bedding planes match and are parallel to the actual hill slope, that's where we're going to get rock slides. So this was 38 million cubic meters of sedimentary rock sliding down. So all of that sandstone block just fell, collapsed, and it creates its own dam, basically. So now they had to completely reroute the river. This happened in 1925. As you can imagine, this area has a lot of snowpack. So as that snow melts, as it gets warmer, we're going to increase the infiltration of water going into the sandstone unit. Sandstone units are pretty porous, so they can take in a lot of water. Shale and limestone, however, shale is really impermeable. It's all those clay materials that get solidified into rock. So once you solidify clay, think of clay pots. You can hold water in them. It's a vessel that you can hold water in since the beginning of the dawn of time. So they're gonna create an impermeable surface where that water is going to pool up. And right on that bedding plane between the shale and the sandstone, you're basically creating a lubricated surface of water along a hill slope. And then you're going to continue to weaken it by eroding the bottom of that unit with a stream channel. You're going to have a recipe for disaster. So not only can we get blocks moving as a unit, we can also get soil moving as a unit. So for soil slip or soil slide, this is where the material still moves as a cohesive block. All the soil, the weather material, everything above the R horizon in our soil profile. Try to remember those horizons too. OAE, BCR. Remember, R is the bedrock, C is the parent material, the weathered stuff. Everything above that is soil. So as this is going to start moving, it often becomes known as what's known as flowage. It kind of moves similar to a fluid. These happen most likely in steeper tilted surfaces. So real steep slopes, like cut banks for road cuts or stream channels, stuff like that. These can happen over days. These can also happen pretty quickly. So these are pretty variable in their speed, but overall they still happen in a short enough time span that it's pretty devastating. So we can get these a lot in, for example, this is Rio de Janeiro. This killed thousands of people. They had a lot of heavy rain in 2011. All of these homes are built on a hill slope with all of this unconsolidated soil all the way up top. So if you have a lot of heavy rain, you're going to end up destabilizing that soil block. It's going to create a lubricated surface where it can just slide. And this happened over like one day, right overnight. Really, really devastating. Destroyed a lot of homes, left a lot of people homeless. So this happened over a period of days. This didn't happen, the change happened overnight, but it still goes on and on. So these can happen at very slow rates to the point that you have to map it out and see where the soil blockage and where the soil creep is happening. So this roadway buckled and shot up 12 to 15 feet. So that's the only road for a certain number of miles, you're rerouting a lot of traffic. It's going to cause a lot of problems. So most of this is caused by rain. Rainwater is going to be really important. Okay, so now we're moving into sliding. So here's where we're still moving as a cohesive block. This is what's known as slump or rotational slide. This is where you have more of a bowl-shaped depression, and you're pretty much all the rock inside of that bowl shape is going to rotate around the shape of that circular depression. So instead of it just falling due to gravity down the hill slope, if you can cut into the bank enough to create a circle, you've created an unstable surface that can just rotate, because the center of gravity on that circular block of sediment is going to want to fall to the center of it. If it's a if it's a half dome shape, it's going to want to shift its weight so that it's balanced. So that's where you get the rotating surface. So this happens, it's the slowest type of slide, but it can happen pretty rapidly. So we have the original surface here, and we have this slide surface, and maybe this was just how the bedding planes ended up deforming, or we're depositing horizontally, but maybe we have some different blind thrust faults that can mismanage the shape of this depression and make it into more of a circular shape. So this is going to sit in there much like half a slice of watermelon. And as you're going to increase the weight on top of it, it's going to want to find its center of mass, its center of gravity, and it's going to rotate to match that. So all of this stuff is going to rotate with gravity down this way, and then all of this stuff that was in this circular depression is going to move out into what's known as the toe. The toe is just the term we use for landslides, mudslides, all the material at the bottom, that's known as the toe. The stuff at the top, that's known as the head. Just helps to keep it in perspective. Use the same terms for glaciers. So the toe of the glacier is the very bottom of the glacier. So the toe of this is going to flow out of this rotational area, out of the circular depression, and it's probably on another hill slope, so it's going to flow downward because now it's unconsolidated sediment. It's going to move as a unit. So whenever we have slump, we usually get what's known as scarps. So this is where those blocks slide off of what's the original surface, and it leaves these like sheer cliff-like structures that you can see. So we can tell where the slumping blocks are and where the land is more stable. And this happens everywhere in the US, and this is what it looks like. It can be very small. This is just from someone's backyard in Delaware. They're on a hill slope. There's probably a circular depression at the bottom here. All of this is starting to rotate over time. Now the cracks can appear overnight, but it's going to continue to slump unless you mitigate. So this is just going to continue to fall until it reaches its state of equilibrium, where it's balanced out. They can also be really large too. So let your eyes adjust to this picture for a second because it takes a little bit. So you'll see, it's hard to see in this room, but there is a person standing up there to the left. That person is standing straight up. So not only did you have this hill slope move this way, the slumping block moved backwards with the rest of it. So all of those trees are tilted backwards. This block moved in this direction. So we ended up with this huge landslide that just basically wiped out this entire section of forest just by tilting all the trees up. This is Whidbey Island. I want you to think about that for a second. It has happened countless times over the past 100 years and numerous times since December. So why would you continue to buy property there? That's beside the point, but we'll move on from there. So one thing that I've learned to appreciate as a geologist is that especially now, since I'm trying to look for a home to buy and look for a property to purchase rather than continuing to rent, I know what to look for when it comes to bad property management, and what could potentially be a problem, like a sinkhole or a landslide or what have you. So it's useful to have a geologist as a friend when you're looking for buying property for sure. Okay, so that's slump and slide. Now we're moving into flowage. So flowage, now we're starting to mix all this unconsolidated material. It's going to behave more like a liquid. They're very, very fast. We're moving all of the loose stuff on the top. So rather than a block that stays together, we're moving like everything, all this unconsolidated stuff. So maybe there's a sliding surface where all this soil is on top of a bedding plane of some rock formation. Maybe it's on top of a piece of shale. It's a nice smooth surface for it to slide. But then we get this separation in between the unconsolidated stuff on top and the bedrock on the bottom. So maybe there's this cushion of air or water or some other type of fluid that's going to help cushion it and give it this surface that it can slide on. So as I said, these are super, super fast. So avalanches are a great example of this. Avalanches are incredibly, incredibly rapid. We have debris flows, which are otherwise known as mudslides, and earth flows. But they can also be happening very slowly. So this is what's known as creep, where the soil just kind of moves slowly, slowly over time. That happens on slopes that aren't as steep. So we're going to talk about each of these. So for earth flows, so this is where the earth is now wet. So we're introducing fluids. It moves partially as a cohesive mass, and it's a mixture of soil, weathered rock, and they move relatively fast. So this is in Russia. This is an earth flow. So this originated from a coal mine. All the coal mine tailings and all the broken up rock, they pile up. And as you get rain, you're introducing all these fluids into those piles. So that'll just continue to flow. So this is at the end, it's starting to settle out. But as you can see, that's a huge, huge mass of rock that you just can't stop. It's flowing into the street. And it's going to continue to do so until there's no more mass behind it driving that force. If you look in the back, that's electrical wiring. Knock that over too. So when you have stuff like that, you have the short-term effects, the immediate effects of that rock slide. Maybe you have some people that got caught in it, vehicles, homes, stuff like that. But then you have the long-term effects of that. That just destroyed a lot of huge, huge electrical cabling. So now you're looking at power outages that may not be able to be fixed for a while. So you have short-term effects immediately after these, and then you have the long-term effects of like dealing with the infrastructure problems that come out of it too. So avalanches, now we're dealing with snow. So the only thing moving here is snow and ice. Sometimes it'll pick up some of the stuff up top, like all that loose rock that falls off as rockfall, but the majority of it is snow and ice. This is moving as a cohesive mass. So remember, snow as it falls as a blanket, much like sediment does. It deposits in horizontal layers, and if you're depositing on a steep hill slope as a unit, you're going to have these weakened planes in the actual layers of snow and ice. So as the snow starts to loosen up, it's going to loosen more at the point of it and then widen as we go down slope. It's going to carry everything it picks up in its path. So these can be millions of tons of snow and ice. These are really devastating and they move really fast. about 60 miles per hour. And these happen everywhere. We've gotten very good at dealing with them, but the only way to deal with them is by causing them when people are out of the area. So they'll use like sonic cannons that send this huge sound blast up there to basically loosen everything up. If you get rid of all of that loose snowpack before people start skiing and snowboarding on it, then you're a lot safer off. So we have thousands of these annually, and we've had them for a long time. So they leave these paths known as chutes that are just where they're cutting down everything in their path. All that snow and ice is cutting down the trees. So they just leave all of these linear features in the boreal forests that are at the slopes of these mountains. So they're really easy to track where they've been in the past. So these are mostly contingent on the slope, of course. So if we have a very steep slope, steeper than 25 degrees, the stability of the snowpack is going to play a really key role. And then, of course, the weather itself. So if we have warming temperatures, we're going to get more melting. More meltwater is going to loosen the stability of that snowpack, as you can imagine. All right, so now we're moving into flowage. So this is debris flows, mud flows, and we mentioned lahars when we were talking about volcanoes. So this is behaving the most as a fluid. So it's not cohesive, it is a big, big mixture of everything. So this is where we're introducing the most water, and they're right in between. If you had a landslide, which is just rock and stuff sliding, and a flood, which is just water, this is a mixture of the two. So because you've introduced fluids in here, these are going to be the fastest moving. Some of them not as fast as avalanches, most likely, just because they have that cushion of air underneath that snowpack. Kind of works like a hovercraft. That cushion of air just gives it something to float on almost. So that's why they're able to move so fast. But water is the key here. It moves like water, so it's going to flow into channels. It's going to take the path of least resistance, but it also has momentum behind it. It has momentum and it has mass. That's going to be key here. So all that mass is going to knock stuff over and with anything in its way. So this is an O3 near Denver, and this is what they look like. So you can see it behaves more like water than it does in those other videos. So it's carrying all of this stuff in it. Those big rocks, all that loose sediment is getting mixed up in the water. And once you're able to pick up all of that heavy stuff, it's going to knock some stuff over too. So this is an aerial photograph of Montecito, California. This is January 9th, 2018. This is taken a few hours later. So keep an eye on certain areas here. So it wasn't just like one portion of it, just almost the entire hill slope turned into a mud flow. So look at all that green up there at the top. Now it is not. So you have to think about whenever you do have search and rescue, you are burying void spaces with a bunch of unconsolidated sediment. So in the same time period that you have subsidence that can create sinkholes, if you have a house that is completely buried by sediment and that house begins to collapse, that can also create a sinkhole over where you're trying to conduct search and rescue operations. So you could potentially sink some of those rescuers into a bad situation. Okay, so here's the slowest type of mass wasting, where we have soil creep. We can barely see this. It's completely imperceptible to us. We're talking millimeters per year. Same rate of movement as your fingernails grow, probably. So this happens on more gentle slopes where we have all these layers of rock, all this unconsolidated sediment on top. So the land surface is going to move a little more rapidly than the underlying geologic forces. So we have a lot of ways that we can at least track these and notice these. So one of these is that obviously if we have a road cut near one of these, we'll have a lot of soil fall into the road. That's going to happen over time gradually. So it'll keep building up and building up until there isn't a shoulder anymore. Also, if you build any type of straight infrastructure like a telephone pole or fencing, it'll eventually tilt because you've put it in straight and that whole soil surface is creeping downward. So it's tilting all of those pieces of wood. And then you have what's known as J curves on trees. Trees always want to grow straight up into the air. So they'll start by growing straight up, and as that soil creeps, they'll continue to curve as they try to keep going up straight. So you can get some pretty intense ones, like you see right along Crater Lake here. A couple of those trees, especially that big one right there, that's a huge J-turn. So that indicates a lot of soil creep, really slow, imperceptible rates of soil change. That guy to the right, that's my PhD advisor. He just looks so happy to be there. But as I'm sure you can imagine, we don't always just have one or a couple of these. These things happen as complex systems. So you can get a bunch of different types of mass wasting all in one event. So we get one or more different types of materials over different sliding surfaces, moving at different rates. So we could have soil creep down at the bottom of this hill slope that could contribute to lowering the pressure holding the rest of that hill slope up. We could have some rotational landslide, creating those scarps, rotating and bringing the toe of that mass out of that depression. And then after it's out of that depression, we can have this translational slide falling down that slope. So these things will interact with each other and create different types of hazards. So this is in La Conchita. This moved around 400,000 tons of material. So you can see the rock fall up top. Right around the middle, there was that rotational slide, and now we're getting into the flowage right near the bottom of it. All right, so why do landslides happen? We have things known as shear stress and shear strength. So shear is basically force of friction. So if I'm pushing down onto this podium, I'm enacting a force upon it. I'm enacting a force in this direction. A shear force is if I was sliding my palm across the surface. I'm enacting a force along that surface in the same parallel direction as the surface. So we have these different stresses acting upon all of these masses of rock and soil, and any change in those net forces is going to initiate some type of slide or destabilization. So this is what this looks like in the simplest cartoon we can have. So we have our slope, we have some object. Let's say this is just a block of rock. So we have our gravitational force, our load or weight. So that one is not going to change. That's based on gravity itself. We have the angle of our slope, our alpha, which is going to be measured right there at the bottom, as well as the angle at which from gravity. We have our normal force. So with every action, there's an equal and opposite reaction. So our normal force is going perpendicular to the surface itself. So that's our Gn. So whenever we have normal forces, more normal force do we have, less likely we are to slide. We're going to build up that normal force. We're not going to slide as much. So GD is going to be our driving force. So this is the force that's pulling the weight down the slope. So the normal force is pulling it into the slope itself. Driving force is pulling it down the slope. So if we have a greater angle, we're going to increase our overall driving force. We're more likely to move down a slope. So this is where we're getting into our sines and cosines. Go back to your trigonometry. So our GD, which is in this direction, is G sine of alpha. So the gravitational force portion, the sine of the angle of the slope. So we have GD in this direction. We have Gn going into the slope itself. We have G pulling down directly from gravity. What counteracts that driving force? Yeah, friction. So friction is going to be moving in this direction. So Fs max is how much overall friction that we have, which is static friction, friction at rest. So Fs max is always going to equal GD until slip occurs. What does that mean? Well, that means that if we have a max friction that equals our driving force, there's no net change. There's not going to be any motion. Now, if Fs max is falls, we're going to have a greater driving force. We're going to move down slope. So if Fs max is greater than our driving force, slide, no slide, or do we not have enough information? What do you think, Adam? No slide. What makes you say that?
The frictional force helps the object from going down slopes. The frictional force in the opposite direction.
That's right. The frictional force, because it's so much greater than the driving force, we're not going to have any motion. It's not going to move it up the slope, because then we're going against gravity, but it's going to keep it in place. It's not going to move any further down slope. So we're not getting any slide. So what if we switch that? Now we have a driving force greater than the frictional force. What's going to happen? We're going to slide. So the balance between the driving force and the friction force is really what's going to dominate whether or not we slide. However, keep in mind that what's going into calculating that driving force is our slope angle, our gravitational force, and obviously the sine of that. So, as we've seen, even though landslides happen near hill slopes, almost every hill slope on Earth, people still live there, live on hill slopes, live next to hill slopes. Why? Because that's nice property. It's good property there. It's still land that we can use. So something that we have to determine whenever we're trying to map out and figure things out if it's safe to live there is what's known as a safety factor. So we can measure our slope stability using this safety factor, which is the ratio of shear stress over shear strength. So the driving force that would pull something down the slope over the resisting force, the friction, the slope itself that would hold that together. So all of this is determined by all of these relationships. what type of earth materials you have, meaning like what grain sizes you're using, if we're working with bedrock or soil. The slope angle is going to be really important. So just the shape of the landscape itself. Climate, that's where we're going to get it's going to impact vegetation and water for sure, just the climate system in general. Vegetation, it can add weight to a hill slope. It can also really root down that hill slope and hold it in place. And water, that's bold, you'll notice, that's the most important one. So just introducing water to a hill slope is going to be probably the biggest one. And then with everything in geology, give something enough time, we're going to introduce some changes to that environment. So if our safety factor is less than 1, we're unlikely to slide. If we're greater than 1, we're likely to slide. So that just makes sense mathematically if we look at this ratio. All right, so how does water create conditions for mass winds? So we've focused on our frictional forces, our driving forces, and our normal forces. How does water impact those? Because that's what's going to drive whether or not there's motion. So by percolating into sediment and rock, we're going to decrease the frictional force. So we have water in between those layers at those fractures. We're creating a lubricated surface for something to slide. So we're decreasing the frictional force. And that's going to, while there isn't a change in our driving force may end up being greater than our frictional force. And then we're going to get motion. We can reduce the normal force. Remember, water is buoyant. So if you create a layer of water at the bottom of that block, you're going to create something for the block to float on, and you're going to reduce your overall normal force. And then we can just increase the gravitational force. Water is heavy. If any of you have ever carried a 5-gallon bucket of water, it is incredibly heavy. I think it's, how many pounds? It's like 3 point something pounds per gallon of water, something like that. Water is very heavy, so if you add weight simply through adding water, you're going to increase your gravitational force. Now that's just from introducing water to the environment. What happens when that water flows out? It's carrying stuff with it. So this is where we have water's erosive capability. So water is going to remove sediment, and if you decrease any supporting material, you're going to decrease this overall stability. That just makes sense, right? If you're digging stuff out from under the road, it's not going to be as strong enough to support that road. It's going to be more susceptible to collapse. So the types of earth materials are going to come into play here too. So this is where we're talking about cementation and consolidation. Cementation, just how stuck things are together. Think of cement itself. Consolidation, if they're the same grain size, if they're blocky and are able to experience more friction. So if we have well-cemented deposits, as you can imagine, they're going to behave like cement. They're not going to fail. They're going to be a lot stronger, a lot sturdier, a lot more stable on a hill slope. If we have a lot of loose stuff, it's going to be more preferential to flow downhill, to fall downhill. So unconsolidated materials on top of bedrock, all that stuff is going to keep falling. So this picture is from Chile. This is one of the areas where we do research. There's a rock glacier right at the bottom of this hill slope. And the reason there's a rock glacier there is because all of this stuff on top, which is known as talus. Talus is all that broken, weathered bedrock that comes from the mountain slopes and falls down into these cones. This glacier used to cover this entire valley, and now it's covered by all of this weathered material. So that's how rock glaciers come to be. They're glaciers that can have a core of ice covered in all this rock material that falls down the hill slopes. So different materials have what's known as a different angle of repose, the steepest angle at which a sloping surface can form. So if you think of, if anybody has driven past a quarry where they're piling all those rocks, they're coming up the conveyor belt and they're coming into that big cone-shaped pile. We figured out that the differences in grain size and the type of material creates a different angle max angle for that pile to form at. So when you have fine sand, real fine grain stuff, small grains, you're gonna have an angle of 35 degrees. It's pretty shallow. Coarser sand, you're having a little less, a little more space in between the grains, so you can build up a little higher. And then angular pebbles, the angularity of these pebbles is going to help, they'll get stuck to each other. You're going to increase the amount of friction that they can have, so they can build up a little higher. So water, once you introduce it, can impact the angle of repose that we have in ourselves. So we have the angle of repose for dry sand. It's that either 35 or 40 degrees, depending on the coarseness of the sand. So you have all of that contact in between the grains. And this is, of course, if this sand was perfectly circular, you have those few contacts between the grains, and then there's airspace in between. If you add water to it, there's a special surface tension applied to water as a universal solvent. It has a surface tension. It will hold things together. It will hold wet things together. So think of whenever you're making a sandcastle on the beach. You add a little bit of water to the sand. Your sandcastle is a lot steeper than 35 to 40 degrees, right? So water helps to create almost like a glue that can help hold these grains together a little more whenever they're built a little steeper. So you'll see there's a lot more space in between the grains themselves, and there's that cushion of water in there. So the right amount of water will add enough surface tension that it'll hold it together. But as you know, if you add too much water to your sandcastle, it's going to collapse. So there's a special point at which the sand will become saturated or oversaturated. That means there's too much fluid. It's going to behave more like a fluid, the more fluid that is in it. So we don't have any contact between the grains anymore. So we're going to behave more as a fluid. So the more water that is in something, the more like water it will behave. So the rock type is also going to play a role here. Think of our igneous, our sedimentary, and our metamorphic. So most people are familiar with shale, that thin, flaky stuff. You get a lot of it in Pennsylvania, not so much around here, but it's really thin, forms in sheets. It's really easy to weather. You can get, honestly, if you pick up a piece of shale, you can break it apart with your hands. That's how easy it is to weather. So if we can do that just by picking it up, imagine slamming water and wind for thousands of years, what that's going to do. So if you have a layer of shale in certain areas, you're going to greatly weather out that area more preferentially than other types of rock, like sandstone or limestone. So those are going to be a lot more stable. Granite, especially. Granite doesn't have a lot of rock falls. Granite doesn't create a lot of rock slides. You'll get some exfoliation from those types of blocks, but most of them are pretty stable. They don't weather very readily like shale does. So that's what forms most of the Grand Canyon. Grand Canyon is just sedimentary rocks everywhere. Billions of years of sedimentary rocks. So because they're sedimentary rocks, they don't have those same chemical bonds that igneous and metamorphic rocks would have. They're going to break down a little weaker. That's why you have such a vast empty space where all that rock was broken down. So we can also increase our instability in the slope by just steepening the slope. So if we keep digging out and removing sediment, we're going to make things steeper and steeper and steeper. And as we increase that angle, that alpha value, we're going to increase our driving force in the overall equation. So after this photo was taken, it's kind of hard to see, but that shadow right below the house, that's empty space, by the way. So right after this photo was taken, the corner of that house fell. So this is a huge problem in California, especially because they have so many houses built on hill slopes, and it really ups your insurance premium, as you can imagine. So which of these increases if we steepen our slope with erosion? Yeah, alpha. That's the only thing we're increasing. We're not increasing the forces. The weight is going to stay the same, but we're increasing the steepness. Steepness is that angle, that alpha value. Yeah. So if you're increasing your steepness, you're increasing your alpha. The alpha is calculated into the driving force. So that's how that train of thought works. So you can also increase your slope by removing material at the base. As you can imagine, if you have just a mass removal of stuff at the bottom, you're going to increase the instability at the top. This is a problem in Pennsylvania specifically. A lot of people live near hill slopes, and there's a lot of use for just bulk rock. If you live near a hill slope, you can dig it out and you can sell it for gravel and stuff like that. A lot of people end up doing it on their own property. The problem is they're digging it out at the base of a mountain, so you have this all this stress is staying the same, but you're decreasing the other stresses that are keeping it in place. So this is where we have what's known as daylighted beds. Daylighted beds just meaning they're exposed to the sunlight, which means we can see them on the surface. So just like we said before, since these are matching that same hill slope, they're parallel to it, they're going to preferentially slide along those bedding planes. So we see this a lot at road cuts, specifically. If you don't plan your road building well enough, you can create a lot of these daylighted beds and increase the instability. So most places, whenever they try to do road cuts, they'll try to go perpendicular to the actual bedding plane orientation, so that you're decreasing that that chance that you're going to have just a completely translational slide. Topography is going to play a role here too, because if we're talking about slope, we're definitely going to have to talk about topography itself. So you guys did a lab a while ago, I'm sure, on topographic relief. So if we have a higher relief, that means we have a higher slope. So steeper slope, greater driving force, greater magnitude of the driving force. So as you can imagine, higher relief we have, the more mass wasting that we're going to have as a whole. And of course, as with everything, tectonics is going to cause it as well. So here we have the subduction zone in the Cascade Range, the Juan de Fuca plate subducting beneath the North American plate, which ended up creating the Cascade Range, the Olympian Mountains, all of that fun stuff. So the Juan de Fuca is diving down beneath it. Because it's subducting down, we're getting this pushing up of the North American plate. So as we're pushing up, we're increasing our topography, we're creating relief. So we're going to increase our slope, and that's in turn going to increase our driving force. We're going to continue to push and push even higher than before. And then we're going to create a pulling factor on the other side of the plate itself. So, and then obviously we can have some earthquakes too in this area that can be pretty devastating and cause even more instability. So that'll help as well. And we see this even today. So this is in Oso, Washington, 2014. So this is a hill slope made from a lot of mostly soil, not a lot of rock at the bottom, but most of this is soil. So heavy rains happened overnight, and around 10:37 a.m., this is where we get that slip. So this mudslide went through the Stillaguamish River, killed 43 people, destroyed 49 homes. Very, very devastating mudslide, and there's still a high risk in that area of mudslides today. Let's talk about vegetation. So we've said before that vegetation is really good to add strength to the hill slope itself. It has those big root systems that are going to hold soil in place. The problem is vegetation adds weight to it. So remember, if we're increasing our weight, we're increasing our force from gravity too. So if we have different types of vegetation that don't have very good root systems, but we're just planting on top of that hill slope, all we're doing is adding weight and not enough actual core strength in the root system. So this is in California. This is what's known as chaparral, which is like this, it's like this shrub, kind of a desert shrub, real thin root systems, not very large, not like trees. Trees have huge, vast root systems, but because they have all of this shrubland over all of these hills, all it's doing is adding weight, not enough root strength. So it's adding weight. It's also bringing in moisture, and all that moisture sometimes gets released into their root systems. So if you're adding water to this, sometimes it can create a little more cohesion. If you add too much water, you're going to create slippage. So knowing the right type of vegetation to use is going to be really important in mitigating these. So just like vegetation can increase the weight on a hill slope, just by building a house is going to increase the weight on a hill slope. So this is the main way that we impact landslide incidents. We build houses on these hill slopes because we like to look out onto a vast hill slope and imagine that we are just a great drug cartel lord looking over their vast empire. So because of this, because we like to build in these areas, we have to create a flat surface. So we cut out stuff from the upslope, we deposit it on the downslope, we create this flat surface, we're increasing the weight, and we're going to increase the risk of collapse. So while we also have cut stuff away to build a surface, we've also cut stuff away if we look down this way to build a road, because in order to build a road, you have to have a nice flat area too. So if we cut through that, we're also going to create the instability, and not just from the actual cutting of the road, but just the action on the road, the constant traffic. If you have a very busy highway going through a road cut, you can have a very high risk of all those vibrations creating instability in the hill slope itself. Remember, liquefaction, whenever we shake unconsolidated sediments, it tends to behave a little more like a liquid. So all of those, even though it's not very much shaking in its magnitude, all of that stacks up. So it's going to behave a little more like a liquid and tend to add to increased soil creep. So there are two ways that we can mitigate. We can prevent or control the active movement. That's going to be done through engineering structures, geoengineering, and of course awareness, which is probably the easiest and cheapest one. Just saying, hey, don't build at the bottom of this unstable hill slope. I don't care how much your housing property is going to be worth. That's a really easy way to do it. So let's start with prevention. So something that a lot of places do along road cuts specifically, it's what's known as rock bolts. If any of you are fans of rock climbing like I am, you've probably used rock bolts before. It's the same basic process, except on a much bigger scale. So if you have, for example, you have that original slope that you see and that road cut, and you have all of that fractured rock on the outside, you can drill into that fractured rock, incorporate a bolt, and bolt that into more stable bedrock on the other side. So you're basically just locking it in place. Even though this looks like just these little bolts everywhere, it's actually really useful in locking that whole fractured bedrock portion in place. I couldn't find the video. I looked it up this morning. I tried to look for it everywhere. There's a video of it's like a sandbox on stilts, and it's just filled with sediment. And they show this guy, he's just putting these rock bolts in these regular intervals in this like loose sediment. And he shakes it, you can see it's really, really loose rock. So he puts all these bolts in, and then he takes out the bottom of it, and then he stands on it. So even just with unconsolidated sediment, just by increasing the pressure with these bolts, you're increasing the pressure that they're feeling, those rocks are feeling on each other. So it creates a really, really stable surface, and they're really useful. So we can use these by themselves. We can also use these with retaining walls. So just having, if you have all this unconsolidated sediment, you can't really bolt stuff in that. But if you have a retaining wall and you can bolt into the retaining wall through the sediment into some bedrock, that's going to help create a much stabler surface. If you've ever driven through Philly, you have probably seen these. These are just fencings that they encase the rock surface on. Whenever you have rockfall, there's not much you can do about it, just because frost wedging, exfoliation, that stuff's going to happen anyway, so it just pops off. But you do want to prevent it from falling into the road, because if it hits somebody, it can do a lot of damage. It can cause an accident. It can really, really screw up your car. So if you just have a netting that kind of slows the velocity of that falling rock, that can really, really help prevent all of that fall from coming into the road. Now, it will also build up at the base of this, so that is something that you have to keep in mind. But if you manage that, if you have some removal crews come out, pick up that rock, you can even use that rock for like use it for gravel, stuff like that. So it can be a really, really effective and cost-effective tool. So let's talk about slider flow mitigation. So we know that water is the main problem here when it comes to landslides and mud flows. So we have to figure out what to do with water and how to get rid of the water and redirect it. So we can drain it in different ways. We can try to prevent water infiltration, rather than, like, remember when we were building retention ponds to prevent flooding, where we wanted all that infiltration, we're going to try to do the opposite. We're going to prevent infiltration, because the infiltration of water, it's what's going to make this sediment behave more like water. And we can also build retaining walls and plant vegetation. So let's take a look at these. So this is probably the most simple feat of engineering ever conceived by man. That is literally just a pipe with holes in it put into a hill slope. How much more simpler can you get? So all it does is lower that overall water table. So the water table follows the same path as the hill slope. If you lower the water table, you're lowering the amount of saturated sediment over top. So if you have the overlying layer is a lot drier, has less water in it, you're going to increase the stability of that slope. So this is a really, really easy way of mitigating that. So we see a lot of these in Cali, especially. This is along Highway 101 in Garberville. This is all shale. So remember, shale is really impermeable, so all that water pools on top of it. So if you drill horizontally along that bedding plane, you're going to drain out all that water. You're not going to have that lubricated surface for stuff to slide on. So, and that's really, really cheap too. This is all PVC. You don't need like corrugated steel or anything like that. Just PVC pipe with holes in it. Really easy, really simple, real cheap. What more can you ask for? We can also just reroute the surface water itself. So if we install, you can see these in Pennsylvania, especially if you're driving up near Hazleton, the Poconos, Carbon County, Lehigh County, you'll see a lot of these. They're just concrete chutes. They send the water down away from the hill slope and directly into a storm drain. So this is a lot easier for them to manage. It prevents the landslides. All that stuff goes into the storm drain, ends up into a retention pond where we can safely infiltrate and prevent flooding. So remember, this is more stuff that we're going to end up having to catch. So whenever we're planning retention ponds, we have to plan for this type of drainage as well. Then a real simple one is plastic sheeting. I've had to use this before when working in environmental remediation. We had a site with, so if any of you are unfamiliar with how heating oil works, you have a heating oil tank in your basement. A heating oil company brings a truck in, they bring out all this hose, put it into your fill pipe, fill her up, and then they retract the hose and they leave. At this point, it happened to be winter. This house is situated on the floodplain right next to a creek. And this is a really pretty steep slope going into the creek. So they definitely have some stuff like this, some slumping going on in this yard. So the guy filled it up and he just detaches it. And there's an auto reel where you press a button, it reels the hose in, but you're supposed to hold the other end of the hose because there's residual stuff in that hose that if you reel it in, it's going to come out. Well, it was really cold that day. The driver didn't really feel like staying outside. So he just hit the auto reel and the entire length of the yard just filled up with all that residual oil. Not a lot of oil, maybe like 10 to 20 gallons, but still enough to cause a huge, huge impact. So not only did that, not only did it get all over the yard, it also killed the vegetation there. So there wasn't any root systems there. So you have all this dead vegetation, and then we have to go in, dig stuff out to remove all that contamination. So we're increasing the instability of the slope. So the best way that we could do without building huge engineered structures was to just put some plastic sheeting up. So all of the rainwater that came up, we kind of created a chute to go over that plastic, flowed over those contaminated areas without touching them. So all the water flowing into the creek was at least fresh precipitation. It wasn't any of that contaminated stuff. So we use plastic sheeting for a number of features. So the best way we can also do it is by reinforcing the toe of these hill slopes. So if we have a retaining wall, remember, if we have a retaining wall, it's going to stop everything. So that includes water. So we have to have some type of drainage, which for some reason we chose the name weep hole, which I'm not a fan of because it just sounds nasty. But you have a real solid foundation built of concrete. You have reinforced rebar going into these concrete blocks. And then you have that drainage for all the water that is going to end up infiltrating. So remember, you want to drain that stuff out. So if you build a retaining wall and you don't put that drainage pipe in, all you're doing is massing up all that water. So eventually that's going to get to the top of that and it's going to flow right over like a mud flow. So retaining wall wouldn't be useful to you at all if you don't have that drainage. Then an even simpler one is just throw a bunch of loose shit at the bottom. This is what's known as riprap. Riprap is just these irregular shaped boulders. They're usually a little bit bigger than your fist. We use these when we're setting up like drainage systems. There was a job site where we had to reroute roof drainage and it was going out onto a hill slope. So we had the drainage go into this area where it had all this riprap. It broke up the current of the water. So rather than creating a channel, it was dispersing it and allowing it to infiltrate without destabilizing and cutting into the slope itself. So whenever you add material, you need to keep in mind that these are going to permit drainage. So it's only useful in areas where you can allow certain types of drainage. You may have seen this before. They have these in off of 422 going into Philly as well. This is what's known as hardscaping, which is where you basically paint soiled cement onto the side of the rock face. In some cases, in very specific cases, this can be very useful. The main problem you have here is cement. After it dries, it behaves a lot like a rock. So all those pressures on the inside are going to be acting on the cement. So if you don't reinforce that cement, it's going to exfoliate, much like a regular rock would. So in certain cases, this is really good. In other cases, it may not be the best option. Plus, anytime this pops off, it's going to come into the road. So then you have to worry about the rock fall. Believe it or not, drivers do not like when pieces of cement hit their car while they're driving at least 70 miles an hour on 422, especially. And then we can also have graded slopes. So graded slopes, it's kind of hard to see from the picture, but that outline kind of illustrates what we're looking at. If we just decrease the overall slope by creating a bunch of benches, that's going to help to stabilize the slope itself. So whenever they're doing terrace farming, which they do a lot of in Southeast Asia, that creates a more stable slope rather than just building right on the slope itself. And of course, awareness and avoidance. So just know what to look for. So daylighting beds. So we have this hill slope here, and we have all of these exposed bedrock formations that we can see are parallel to the slope. We also have all of this rock fall and rock debris at the base of the slope. The presence of debris indicates that in the past, it's been falling off the mountain. So what's to stop it from falling off in the future? Remember, the principle of uniformitarianism. The present is the key to the past. Same and vice versa. So we have all these large boulder fields that can indicate some falling debris. If we have linear paths of vegetation being cleared out, that can show us that there was like mudslides and debris flows in the past. So that's stuff to keep in mind. If any of you ever go out near Johnstown, Pennsylvania, the dam that famous Johnstown Dam that has flooded so many times to the point that Johnstown is known as Flood City, it's still there. One of the features that you can see is that, so it's an earthen dam, meaning it has a lot of soil, clay, it has a clay core to prevent water from seeping through. But the entire slope of that earthen dam has the same exact slope as the bedrock formations that you can see on the side of it. So you're looking across the dam, you see the bedrock formations, and you see the dam is matching those bedrock formations. It's going to collapse again, is what I'm saying, basically. So if there's anything you take away from this class, it's that don't buy property in Johnstown. Other things we can look for is these crescent-shaped cracks. Remember, those are the scarps that form from slumping. Any irregular land surfaces. Remember, land forms based on geologic processes. So don't just think, oh, that's how the land is always going to be. It's formed that way. So it can always go under different changes. So this is in Whitby, England, right after that 2013 slide. There was a church graveyard right in the back of this church, right where the landslide happened. So they actually had really old bodies falling out of the sky onto the houses below, which was not pleasant, as you can imagine. So they had to do, there was a huge cleanup process to not only get all of the human remains back, but also make sure they had the right owner. So that was a difficult and expensive process as well. Other things to look for, tongue-shaped areas of bare soil. So it forms in these like lobes that you can see from aerial imagery or just some regular photography. We mentioned linear paths of cleared vegetation. So this is a hotel on Lake Garda. So that is an engineered structure going from the top. That is just a conduit for everything. So building at the base of that is probably not a smart idea. And then of course, since we're geologists, we're gonna map this stuff out. That's gonna be the best way to create and understand where areas of high risk are. So just like how we have flood risk maps, we can have the same thing with landslide and hill slope instability maps. That's going to tell us locations that are more susceptible or less susceptible. to landslides, and that can help us determine good safety factors, good risk management. There's always going to be some level of risk wherever you are in the world for a geologic hazard. It's all about managing that risk and differentiating between the perceived risk versus the actual risk. So that's really what geologists do in the public sphere. All right, so let's do a quick review. Which factor determines the type of mass movement that will occur? Rock type, soil grain size, slope, water, or all of the above? Everyone? All of the above, that's right. Now, which one of these will affect it the most? Water, yeah. The introduction of water is going to be really important here. Okay. I think that's all I have for today. I think tomorrow, let's see. Yeah, I don't want to start the rest of this today. Tomorrow, we're going to be talking about super fun stuff that we can't prevent. We're going to be talking about bolide impacts and extinction events. So meteorites, so real fun stuff. So that's what we'll do next class. And then I think we should be able to finish that Wednesday. Thursday, we'll probably have a review session because your exam is on Friday. This was a lot of stuff to cover in a short amount of time to study for it. I want you guys to be set up for success. My goal is for you guys not to fail this class. So we'll do a good review session on Thursday, and then Friday our exam, and then sayonara. So have a great Tuesday, everybody.